This video explains the session layer, which is the fifth layer in the Open Systems Interconnection, or OSI model. The session layer is responsible for establishing, managing, and terminating sessions between applications. The session layer has primary responsibilities, which includes establishing communication sessions, which means initiating a connection between two applications so they can start communicating. It also maintains session continuity, which involves keeping the session alive and functional for the duration of the data exchange. It's synchronized data exchange, which manages the flow of data to ensure both applications are on the same page and no data is lost or misinterpreted. Further, it controls dialogue between applications, where it decides which application can send data at what time, preventing conflicts and ensuring smooth communication. Finally, it terminates sessions gracefully, which involves closing the connection in an orderly manner, ensuring all data is delivered and resources are released properly. Now consider two devices, a laptop and a desktop, aiming to establish a session connection. This connection involves three primary phases: establishment, where the session is initiated; maintenance, where the session remains active and data is exchanged; and termination, where the session is gracefully closed. Session establishment initiates communication between applications by negotiating parameters, such as a session identification, transmission mode, and synchronization points. It authenticates users or applications when required, establishes rules for data exchange and dialogue control, and it creates checkpoints for potential recovery. The session establishment process involves a three-way handshake between a client and a server. First, the client sends a session request to the server. Second, the server negotiates parameters and responds to the client. Finally, the client sends a confirmation to the server, and the session is established. Key features of session maintenance includes dialogue control, where it manages which device can transmit data at any given time using half-duplex or full-duplex modes. Synchronization, where it establishes checkpoints for recovery in case of failures or interruptions. And token management, where it controls data transmission rights in half-duplex communication by passing tokens. Now consider a client and a server maintaining a session using full-duplex mode, allowing simultaneous data flow. During this session, checkpoints are established to ensure data integrity. A token is used to manage data transmission rights. This token is exchanged between the client and server. The communication modes include simplex, which is a one-way communication where data flows in a single direction only; half-duplex, which is a two-way communication where only one device can transmit at a time, controlled by tokens; and full duplex, which is a two-way simultaneous communication where both devices can transmit and receive at the same time. Token management controls which device has permission to transmit data in half-duplex mode. Now consider two devices, a client and a server in half-duplex mode. A token determines which device can transmit data at any given time. And also consider two devices, a client and a server, in full duplex mode, where data can be transmitted and received simultaneously. The synchronization points involves major synchronization, which establishes checkpoints where all previously transmitted data is confirmed as received, and minor synchronization, which creates intermediate checkpoints for partial data confirmation. The recovery benefits are that it resumes from the last checkpoint after failure. It prevents complete data retransmission. It maintains session integrity, and it improves efficiency during interruptions. Now consider a client and a server exchanging data. Both the client and server establish synchronization checkpoints along their timelines. In the event of a failure, recovery occurs from the last known checkpoint, ensuring no data is lost. The types of session termination includes orderly termination, which is a graceful closure of the session. All pending data is transmitted. Both parties agree to end the session and resources are properly released. Abrupt termination, which is immediate session closure, and it may result in data loss, typically due to errors or timeouts, and resources may not be properly released. For resource management, it releases network resources, frees memory allocations, updates session status in applications, and prepares for potential new sessions. Now, consider a scenario with orderly termination where a client sends a termination request to a server. The server sends an acknowledgement, and the client sends a confirmation, resulting in the session being terminated. In a scenario with abrupt termination, a client sends an abort request due to an error, leading to immediate session termination. The session layer manages communication sessions between applications. It handles session establishment, maintenance, and termination. It provides dialog control through simplex, half-duplex, or full duplex modes. It implements synchronization points for recovery. It ensures orderly data exchange between applications, and it bridges the gap between application and transport layers. Some of the common protocols in Application Programming Interface, or APIs, are Network Basic Input-Output System or NetBIOS, which provides session services for Windows networks, Remote Procedure Call or RPC, which enables program execution on remote systems, Structured Query Language or SQL, which maintains database sessions, and AppleTalk Session Protocol or ASP, which manages sessions in Apple networks. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.